Hello everyone, this is Varun. Welcome to Aerospace Structures. Today we are going to discuss about the unit load methods in structural analysis. Consider the framework of a figure, that is, I have given the figure in the next slide, in which we require say to find the vertical deflection of point C. This is a schematic of our structural element, and our main aim is to find the deflection at a point C. When you observe this truss, it is acting upon by number of loads n, and it is constrained at two ends, one at A and at B. As a result, entire system is in equilibrium. It doesn't say either it is in static equilibrium or whatever might be, but it is in equilibrium. And now what we are finding, what our main aim is to find the deflection at point C. Now what we do is that we place a load at a point C, that is of magnitude P, F, C. Okay, this is called as a dummy load. And after placing this load PFC or simply PF, we are writing the complementary energy. And the complementary energy, here you can identify there are n number of loads, and you can identify, and moreover there are k number of elements, and the total complementary energy of a system can be written as C equal to summation I equal to 1 to k, because there are k number of elements, and integral 0 to Fi lambda I dFi minus work done by the individual elements, that is R equal to 1 to, since there are n number of elements and summation running from R equal to 1 to n, delta R corresponding to virtual displacement of member R and PR. This is the complementary energy for a given structural system, which is consisting of k elements and n number of loads. And for stationary value of P, and the condition for stationary value of P is dou C by dou PF equal to 0. That is, and for stationary value, that is with respect to load, the differentiation of complementary energy with respect to load or a specific load is 0. What we can say is that dou C by dou P or PF equal to 0. This is the condition which satisfies the stationary value. And moreover, lambda I is given as an extension of an element I due to some load. And when I differentiate this complementary energy with respect to some load PF, what I get is that something dou C by dou PF equal to sigma I equal to 1 to k, and lambda I dou Fi by dou Pf minus delta C. Here, this is one of the most important term, that is the element dou Pf by dou Fi by dou Pf. This is the change in force with respect to the when, for example, when we take a struct like this or some structural element like this, when we apply a load of say P1, and we are observing the behavior or the load in an element I, say this I, because of this load P1 or P2, what I meant. For example, if we apply some other load P2, then it is called as dou Fi by dou P2. That is the change in force in an element due to a specific load. Okay. Now, when we differentiate this element with respect to some specific load, then the only variable which is remain is delta C. When I equate it from the law of conservation of energy, then what we can say that it attains a stationary value. That is, either it might be a maximum or a mean, not a global maximum or I can't say that it's a global maximum or global minimum, but it might be a local, it might be a local maxima and local minima. And this is a schematic, and you can observe that. Now what we do is that delta C equal to can be written as follows. That is I equal to 1 to k lambda I dou Fi by dou Pf. Let us look into what is this dou Fi by dou Pf and its physical significance. Now what we do is that we replace the load P with a unit load at a point C. In the above diagram, what we are doing is that we are applying a unit magnitude of load Pf is equal to 1. This unit magnitude might be 1 ton or might be 1 kg or whatever it might be, but it should be a unit load. And finally, the load in the ith linear elastic member would be Fi equal to dou Fi by dou Pf into 1. This is the force acting in ith element because of unit load Pf, of unit load. That is, here we have replaced the load Pf with unit load. This is one of the most important. And dou Fi by dou Pf, the term dou Pf by dou Pf is the load in ith member due to a unit load at C. When you for example, when you consider an element, when you apply a load, a unit load, that is in the ith member, it is the load which is acting in ith member because of unit load at point C. This ith member might be either this element or this element, this element. When we apply a load at this point and the load is distributed in all the elements, I doesn't say it is a uniform distribution, but there will be a distribution. Okay. Now what we can say is that delta C, when you replace this dou Fi by dou Pf in the above equation, and already the extension term what we know is lambda I is equal to something Fi Li by Ai and Ei. E is the Young's modulus and A is the cross-sectional area of a element. F is the load acting in an element and Li is the length of an element. When you substitute this Fi in the above equation, that is dou Fi by dou Pf in the above equation, what we get is lambda C equal to sigma I equal to 1 to n 1 to n, that is n number of elements Fi comma 0 and Fi comma 1 divided by Ai Ei into Li. This is the deflection formula for a unit load method. Here Fi comma 0 corresponding to the loads existing in a structure and Fi comma 1 is the load because of unit load. Now already it has been clearly written, that is Fi comma 0 is the force in the ith member due to actual loading. Fi comma 1 is the force in the ith member due to unit load. Next, proceed. Okay, if you take a realistic problem, this is one of the problem in space, and what you observe is that there are elements from A to B B to C, and C to D in XYZ plane. From A to B, the length is L, and B to C and C to D is also L. And now at the tip end, we are placing a unit load of magnitude 1 in the direction of both X, Y, and Z. And from B to C, there is a uniformly distributed load, and the angles is 90 degrees. And our main aim is to find the component of displacement at the free end in terms of E and GJ. I'm not going to completely solve this, but I'm going to give the procedure to solve this. Okay, since the cross-sectional area A and modulus of velocity are not given, and what we have is only the EI and the GJ values, that is fractional rigidity and torsional rigidity, but the area and the elastic E was not given. And what we are doing, that we shall assume that displacement due to axial distortion are to be ignored. That is, the displacement due to the axial distortion, that is will be ignored. We place in turn a unit load and assume positive direction of XYZ. And moreover, at the tip, we are placing a unit load in the direction of X, Y, and Z. And first consider displacement in the direction parallel to x-axis. And what we are doing is that we are considering the displacement in the direction of x-axis. And what we can write is delta x equal to integral taken along the length L, m naught, this is, and m1 divided by EI ds, plus ds is a line element along the L, T naught. This is a torsion, T1 divided by GJ ds. We are going to apply this formula to a given structural element. And what we do is that we make a table and we make a plane CD, CB, and BA. You can identify what is CD, CB, and BA. And moreover, M0, we have a table of M0, M1, T0, and T1, XY in the plane of XY, XZ, YZ, so on. And let us consider CD because of load M0. In an element of CD, that is CD, since we are neglecting this load, we are not considering this load right now. And moreover, when because of unit load, there might be a deflection at this point, but there is a no movement either at this point or at this point. And what we can say is that for a CD, along the direction of in the plane of XY, YZ, ZX, and other plane, both are 0. That is the reason we have taken 0, 0, 0. And let us consider about CB, the point CB. When you consider a point CB, there is a unit load of magnitude W along the length L. And moreover, when you look along this direction, and what we observe is that the plane is in ZY plane. Okay. And what we can say is that here we have a uniformly distributed load like this of length L, of intensity W naught per unit length, and the total magnitude of load is WL. But in the plane of XY, here our system, that is the CB, is only in the plane of YZ, but there is no load acting in the plane of other two planes. That is the reason why it is 0 in the other planes. And finally, what we get is that total magnitude of load at a point Z. delta z is W into delta z and into delta z, or simply a small element of z. What we can write is finally the magnitude of load Wz into moment which is acting at the center z square, sorry, z by 2. Finally we get Wz square by 2. In the plane of yz, we have a moment m naught of minus Wz square by 2. And in other two planes, because of element Cb, it is 0. And let us analyze what in BA. When you observe the element BA, along the BA, when you observe this BA, it is in the direction of x, y. And this unit magnitude of load can be applied at this point of magnitude W into L. As a result, when you take an elemental section of x, we can easily write as WL into x. In other two planes, m naught is 0. That is, in other two planes, m naught is 0. And similarly, we can write for m1 t naught and t1. And finally, the deflection delta x can be written as integral 0 to L minus WL square x EI dx. After simplification, what we get is minus WL square minus WL to the power of 4 divided by 2 EI. Similarly, we have deflection in delta y and delta z. This is the end of these sessions. Thank you very much. Once again, this is Varun signing off.
Like, share and subscribe. Hit the bell icon for more updates.